Thank you very much for the kind introduction. And as I was saying before, it's a great honor to be here presenting these results to you guys. So thank you very much for having me. Indeed, I'm working in the team of Christian Schneider. I would like just to add that soon next year, I am moving to, let me see if I can pass the slide, to Madrid. I will start there my own group, where I would like to follow as well several different directions, some of them related to polaritons and some others more related to quantum optics with quantum dots. But yeah, what I'm going to present today is exclusively research that has been done in the group of Professor Schneider. Maybe just a few words first of the university that I'm coming from, Oldenburg. First, where it is located. It's very far away from everything. It's 80 kilometers away from the North Sea, between Bremen and also Groningen in the Netherlands. It's a very flat area, as you can imagine, but it's beautiful. The university is fairly new. Yeah, I think it's one of the newest universities in Germany. I think it was built in the late 60s or so. The design, as you can see, is a little bit particular as it was the architecture at that time. You can see here our labs. This is where we are doing magical research. The university takes the name from Carl von Ossietzky, that is a journalist that got the Nobel Prize during the Second World War or so. He was basically incarcerated by Nazis at that time because he was the one who informed some international authorities about the rearming of the German government before the start of the Second World War. And he died in very bad conditions in prison for being a traitor to the Nazis. Next, the area is also very beautiful. You have the Frisian Islands here on the north. So if you have the chance to come here for holidays, it's something that I can recommend. It's not as hot as Greece, obviously, or Spain, but it is indeed very, very beautiful. And also a very last funny thing, I don't know if you know, but in Oldenburg, there is the House of Oldenburg. They are very much related to many different dynasties of kings in the north of Europe. So I was pretty much surprised to know about this when I came here. Good. So this is the team. Professor Christian Schneider. We started the group in July 2020. At the moment, we were also Lucas Lachna, who's a PhD student in the group, and myself, together with Ulf, which is our technician. Then Han-Yong San came from China with a collaborative grant between Germany and China. He is being the main actor for the results that I will present at the end of the talk. Then we had Bohan. They both are postdocs, also coming from China, but he did his PhD in the group of Urbacek in France, and they are basically the expert ones in 2D materials. And then after we have Martin Hesman, that he did his PhD here, but we were working together in France. He was working at the time on photonics with Daniel and Fuyuki Kimura. And then this master student, Niels, that is the one mostly researching now on strong coupling using M-Cherry as active material. We are having very nice collaborators spread all over the world. Maxime Richard in Institut Nel, I will be commenting a little bit of recent results that I got with him in September before I'm starting into discussing the condensation experiments. In Vienna, the group of Heidelberg, which is the person, Heilenberger, sorry, which is the person that is helping us to grow the top mirror, the electric top mirror via evaporation. Of course, our former colleagues from Rzburg, the group of Sven Huflin and Sebastian Klemm. The theory part is mostly always done by Kenny Setup from the group of Alexei Kavokin. The crystals of TMDCs are generally provided by Sefatin Tongai, and then the HBN, the hexagonal boron nitride, ultra high quality material is provided by the groups of Watanabe and Taniguchi, as most of everybody in the world. Okay, I have prepared 2 slides introducing polaritons. It's a little bit ridiculous to do this to you guys because I guess that you are pretty familiar on the topic. But basically, I'm gonna explain experiments in which light and matter couple strongly. The active material that I have chosen is a 2-dimensional material that I will explain a little bit more in detail. And light is coupled between two dielectric Bragg mirrors. In these conditions, the exciton mode and the photon mode, they externally couple to each other. I had here a video prepared, but it doesn't work. Let me do it like that. Here we can see different detunings between the exciton and the photon, and we can see how the strong coupling arises at this point. So in the momentum space representation. Let me go back to the presentation mode. So exciton-polaritons are interesting because they can occur at elevated temperatures due to the low mass of polaritons, which comes from the photonic part, and it brings interesting properties due to the interactions and nonlinearities, which is arising from the exciton part. There are many other properties that can be studied related to the spin and also the topology phenomena that now is very intensively researched in many different groups, including the one of Professor Lagudakis. As I was saying before, during the discussion before the talk, I was doing my PhD on polaritons. Then I left for 5 years and I was doing quantum optics with quantum dots. I left the community of polaritons, and then I went back and I realized that now the polariton community is not anymore only 3,5 or 2,6 semiconductor materials, right? There is a huge plethora of different systems where you can see strong line matter coupling. And I'm including here some reviews where people are explaining the different platforms in which now polaritons are being exploited, with many different versatile applications that go to very exotic applications, such as, for example, controlling chemical reactions with different materials. I found this recent review from Wang Hanyel in ACS Photonics, where they are discussing in detail some things about polariton chemistry. And it's not only multi-platform, it's not only about many different applications, it's also what we are expecting in the future. So there are many different proposals for simulating different types of Hamiltonians, which is something that is mastered very well as well in the group of Pavlos Lagudakis. There is also a very challenging, interesting proposal from Kavokin to implement a polariton qubit. And there are also some recent applications for transistors and APDs. Correct me, Pavlos, if I am wrong, but your recent Nature is basically about making an APD with polaritons, right? Is that correct, or you would say it in a different manner?
That is one possible application. Okay,
because you can detect in a single photon level, right? And yeah, then there is also this eternal application or possible field of study or relating polaritons to different phenomena such as black hole simulation and Hawking radiation, which could be pretty interesting, I guess. Because I'm coming from the quantum optics community, I would like to highlight here a couple of works that I like very much because they are related to single polariton physics, which is the strong coupling between a single quantum dot and an open cavity, which was done in 2019 in the group of Warburton in Basel. Some pretty impressive work with a cooperativity reaching values more than 100. And also this other work from Sangdokdar in the Max Planck Institute, where they have also reached the single polariton regime, strongly coupling a single molecule with another open cavity. Good. So now I go back a little bit to my research field, which is polaritonics with TMDCs. I am highlighting here this review work from Christian Schneider that he did with Glasov-Korn, Huflin, and Urbacek, where we can see that polaritonics using two-dimensional materials has expanded also into different directions, utilizing different types of cavities, from open cavity, hybrid cavities using metal and dielectric mirrors, linear grating cavities, and so on. A few words about 2D materials. It's the atomically thin transition metal dichalcogenides is a material that is composed by a metal from this group. In general, we are using either MO or tungsten, which is chemically constructed with another element from the chalcogenides, selenium, sulfur, or tellurium. The peculiarity of this material when it's grown in bulk is that it's formed with different layers, which are attached to each other with van der Waals forces, and it's also the reason why one can exfoliate them relatively easy. In general, it's not extremely, it's not correct to call them atomically thin materials, because as you can see, a single layer contains 3 atoms. So it's a thin material, but it's not atomically thin, so to say. The structure is hexagonal, as you can see here. It mimics pretty well the physics of graphene as well. And what is peculiar with this material is that in bulk, there is no direct recombination. So the material is not emitting light, as you can see here in this graph. And when you exfoliate it up to the monolayer, then there is a direct bang gap, and you can have an optical transition, which is here very well highlighted, and it couples very strongly to light. For the sake of curiosity, I can tell you how we are producing these 2-dimensional layers. This is a microscope from HQ Graphene, where we are basically looking for monolayers and then stacking them. Everything starts with Scotch tape. It's as simple as that, which is then the Scotch tape deposited on a PDMS film. Once the monolayers are deposited on the PDMS film, they are transferred into a substrate, which in general is going to be the bottom mirror of our cavity. And then if you are lucky enough, you will find a sufficiently large piece of monolayer that then you can finally assemble with a top mirror to study polariton phenomena. With a proper AFM image, you can even see the internal structure of the 2-dimensional material and see that it's resembling this hexagonal lattice. For the cavity part, even though I will explain later in detail the composition of our 2 different samples that I will discuss about, for assembling the mirrors, we are using normally commercial mirrors formed with silicon oxide and titanium oxide. But in order to fully assemble the cavity, what we do is simply to scratch the mirror itself, take the pieces apart, and then follow the same procedure as with the PDMS. We assemble it fully, depositing it on top of the monolayer. And this helps us to form a cavity. The fine adjustment of the thickness of the cavity is done with PMMA, which requires a previous calibration so that we can control very well the thickness of the cavity in the nanometer scale. Good. There are, and this is, I forgot to mention, these are the typical quality factors that we will get with these cavities, around 4,000 also. They are not incredibly high, but sufficient enough to observe strong coupling. There are different properties that are very interesting or very peculiar to TMDCs. One of them is the exciton binding energy that is relatively large, and it allows to have excitons at room temperature. Also, another important properties of TMDCs is because they have a peculiar crystalline arrangement, you have optical transitions which are circularly polarized in one sense or the other, depending on the position on the reciprocal space, K plus and K minus. And finally, one of the big differences with respect to the semiconductor materials is that they are relatively cheap to produce, and the line width, the oscillator strength that we get with them is relatively high. We have here the record of the thinnest full width at half maximum that we have got with MOSE2. This is of course the record of our expert Bohan, which is our quantum artisan, in which we have managed to get this good exciton emission from an MOSE2 monolayer encapsulated with HBM recently, which is definitely important to save money and to be also fast in the implementation of different samples. I think it's much more efficient than having an MBE, definitely. Good. So among these different nice properties of TMDCs, I would like to discuss a little bit more why we believe that TMDCs are interesting for polaritonics. And this goes back to the discussion of interactions. One of the big efforts of the community has been to demonstrate the single polariton blockade, where basically it's telling us that when you are having one polariton in your system and then you try to add a second one, that transition will not be possible because two polaritons interact with an energy U, and then the second photon cannot be absorbed. So you can have a sensitivity in the single photon region. TMDCs can be interesting for this purpose because the potential of interaction of excitons within a two-dimensional material is not the same as the one that you would find in standard hydrogen excitons. In a two-dimensional crystal, there is these famous papers from Ritova and Keldysh where they were predicting that the interaction will not be Coulomb between excitons. It would follow this peculiar potential in which at very long distances, it resembles pretty much Coulomb interaction, but at short distances, this goes as minus logarithm of R, which changes completely how excitons are going to interact. Because they are confined really in a two-dimensional plane, the dipole is not screened, so you have these lines which are not filling, or they are not screened from other electric fields, and it makes in the end stronger oscillator strengths and stronger two-body interactions. So there are two important things to consider in the following. Let's compare first what it will be the interaction between excitons in semiconductors and in two-dimensional materials. For standard semiconductor quantum wells, I'm talking about hydrogenic excitons, Gx, the interaction between excitons is, of course, the binding energy times the Bohr radius, which can be re-expressed as something that depends exclusively on the reduced mass. And for gallium arsenide, for example, we keep these numbers in mind. We have a Bohr radius of 10 nanometers, relatively large, and the binding energy is tiny. It's only 5 MeV. This basically makes the following effect, is that we will have large Gx at very low temperatures, at very, very tiny Gx for room temperature. Instead, if we are considering non-hydrogenic excitons, that is to say, those created in TMDC, we are having now binding energy that is much larger, it's 2 orders of magnitude bigger in the case of MOS2, and a Bohr radius that is much smaller, only 1 nanometer. And the product of these two things is going to make, in the end, Gx that is slightly larger than for hydrogenic excitons in semiconductors. Not much, it's only 30%, but it's sufficiently interesting to research on it. The other thing that is important or peculiar in TMDCs is the screening or the quenching of the Rabi splitting when we start to add more and more polaritons into the system. And this is something that this is described by GS, and it's something that has been recently studied in a collaboration between Christian Schneider and Maxime Richard. And this was the first experiment that I wanted to discuss about because in September, I went to France and I was doing some experiments in collaboration with Maxime, where we were basically observing how faster TMDC excitons quench the Rabi splitting when they are in a polariton system. So in this graph that I'm taking from this recent paper from them, they are representing the dependence of Gx Coulomb interaction between excitons as a function of the reduced mass. And you can see that for MOSE2, which is the material that they studied in this, that we studied in this sample, it's a MOSE2 monolayer, and that is embedded between two top and bottom DPRs with a PMMA, and then this forms a polariton. They characterize that the Gx interaction is only 30% higher than what an equivalent semiconductor hydrogenic exciton would show. Instead, if we are looking at the fermionic saturation of electrons and holes, we are getting a value that is relatively much larger. And this is basically telling us how polaritons are going to feel non-linearities. If we look at the equations, this is how they enter into the game. Gx is here depending on the density of excitons, and is basically physically detected as a blue shift in the energy of the exciton, and then Gs is something that reduces the splitting, so basically quenches the splitting between the upper and lower polariton. These experiments that we performed were done in a transmission setup. So basically it consists on sending femtosecond pulses that can resonantly excite both upper and lower polariton. And we were studying as a function of the pump power, how the transmission spectrum of polaritons change. So what you see here, for example, is the transmission spectrum as a function of the energy for two different polarizations of excitation, H, polarization and circular polarization. And you can see that, well, this is the spectrum of the laser, as you can see here, and you can see a very clear doublet splitting between the lower and upper polariton branch. At the moment, we were studying all these experiments as a function of the polarization of the resonant laser, because we believe that could be interesting. And you can see here that if we build up this function as a visibility between the transmissions for the horizontal and circular light at low power, we get basically no difference between the two. Instead, if we are starting to increase the resonant driving field of the laser, we start to see that the lower and upper polariton branches, they start to collapse, and we see some strong oscillations. And when we represent these oscillations with this function, that is this visibility between polarizations, horizontal and circular, we start to see this fast oscillation, with oscillation in energy, with we associate of having a dynamical quenching of the Rabi splitting within the cavity while the laser is passing. I am showing these results. It's the first time that I'm showing them. I think that they are interesting and that they are representing a peculiarity of TMDCs, but there is still theory on the go from the group of Anna Mingucci, and we are trying to understand very well how these results could be compared or can be of any difference with respect to other results in the past that date back from 1998. The quenching of the Rabi splitting in standard semiconductors or standard semiconductor polarities is not a topic that has been pretty much studied. You can correct me if I'm wrong, but we only found this paper from Udre from very long time ago, where they were giving an explanation that we are not pretty much agreeing on it. So, we are taking back again from the box all these things that we were studying in the past and trying to see or to understand a different flavor with TMDCs, which could be radically different due to this very different value of GS. Okay. Now, going to the topic on bosonic condensation of polaritons and taking a step back in history and highlighting which were the benchmarks for heralding the bosonic condensation of exciton-polaritons. In this paper, they were exciting non-resonantly a microcavity formed with cadmium telluride, and as a function of pump power, they observe completely change in the dispersion relation of polaritons. There are three benchmarks that in general we are going to be interested in order to see signatures of condensation. The most important one, or the first one, is the input-output curve, where we will be looking at the spectral properties of the light emitted from polaritons. First one, the nonlinear increase of intensity. We can see here in this log-log scale how the intensity is changing slope as we increase the pump power of the non-resonant laser. We will also observe a reduction of the line width from polaritons, which is associated to an increase of coherence of the system. And then we will also observe polariton interaction, which should be explained which is seen as an overall blue shift of the emission. In TMDCs, you have to be very careful with the third one, because increasing the pump power in your system in general might not be associated to a very significant blue shift of your polariton emission, but to an accumulation of charges, and it's a totally different thing. So when we are looking to blue shifts with TMDCs, when we are trying to do this input-output curve, we have to double check many times whether this is a real polariton blue shift or it's just another phenomenon. This is normal because, as I was showing before, GX is pretty similar to the one that we would expect with semiconductors. So it's only the quenching that is radically different. Good. The second thing that one should be looking at carefully is about the thermodynamical properties of your emission. As a function of pump power, you should see that at high pump powers, your distribution resembles a Bose distribution. As you can also see here for the highest pump power, that this resembles very much this exponential renormalization of population. And finally, the benchmark or the most important signature would be the appearance of macroscopic coherence. basically all your polaritons lie on the same state of light, and it can display interferences that are generally studied in using standard interferometry. So for the next experiments that I will show, we will be looking mostly to the spectral properties and the coherent emission. From a paper in 2016, Schneider, when he was starting to get into the topic of polariton condensation with TMDCs, he studied the standard parameters of TMDC excitons, and he saw that it was a very promising material in order to get polariton condensations even at room temperature. So this is precisely what I will be discussing today. Two experiments in which the first one was done at cryo temperatures 4 Kelvin, and a second one using a different type of material that was it was done at room temperature. So for the first experiment, we are using a sample which is a hybrid cavity. It's composed by a bottom DBR, which is aluminium arsenide, aluminium gallium arsenide. This bottom mirror has given us a lot of problems because it contains a gallium arsenide quantum well, in which most of the reference of most of the criticism in the talks, they were telling us that probably this quantum well was contributing to the condensation. But all the experiments, all the test experiments that we have done have allowed us to confirm that the role of this quantum well here was not relevant or was not contributing to the obtention of polariton condensation. The reason for having this quantum well here dates back from a different project that was within the group, in which we wanted to study the drag force of polaritons when you pass a current below. So the fact that there is this quantum well here, I just want to say that it's not for cheating or making condensation easier. Originally was a totally different reason. The active material that we are using is a monolayer of MOSE2, which is encapsulated with HBN, and then we put on top this PMMA, which is setting the correct thickness of the cavity, and then finally the sample is terminated with a top DBR, which is composed by SiO2 and TiO2. You can see here, this would be the bottom mirror, what you see in blue. The monolayer area is highlighted with this dashed yellow line, and the top part of the cavity is this part here that it looks like an iron. Okay, and it has a size pretty small. This is about 4 or 5 microns times 10 roundabout. So what we do first is to study the dispersion relation of the emission. This image that you see here has been done in two times. First one, this one here has been exciting very non-resonantly, so with a green laser. And we can see with powers, and what we can see here is the cavity mode crossing the gallium arsenide quantum well. So this is why you have these two shiny points in these positions. This has allowed us to fit very well what is the photonic mode, which is this parabola that you can see here. And then the MOSE2 exciton is located at this energy, which has been pre-characterized before assembling the cavity. I am indicating here the quality factor of the cavity that we are obtaining. This one was pretty low, only 500, and an MOSE2 line width that is around about 1.5 MeV. It's quite large. From this, we have applied the standard two-couple oscillator model that I was highlighting at the very beginning of my talk. I don't know if I can reach the slide right now, but basically it's the fitting of these two modes. I don't find it now. Well, it's okay. This is just a standard fitting of the two modes, exciton and photon, with a given Rabi splitting. And these are the two new modes that we find, the upper polariton branch and the lower polariton branch, with a Rabi splitting of 25 MeV, which is pretty much what you can find in the literature in other groups where they have been reporting strong coupling. The polariton lifetime is radically much shorter from what we are used to in other 3-5 systems. Is around 210 femtoseconds. The excitation scheme that we are following for these experiments, in which we are reporting bosonic condensation, is a pulsed laser, picosecond pulsed laser of around 10 picoseconds, which is exciting right on top of the upper polariton branch and right below the gallium arsenide quantum well. what we have done very, very carefully, and I will go on that on the next slide, is to make a PLE in the lower polariton branch. We have been looking here at the amount of light emitted from the lower polariton branch while scanning resonant laser all over these energies. So what you can see here is a standard PLE spectrum of the lower polariton branch, and you can see that when we are crossing the gallium arsenide quantum well, there is not a significant enhancement of the lower polariton branch. This is allowing us to discard any significant contribution of the quantum well for the condensation of polaritons. Only when we are hitting the upper polariton branch is when we are seeing a much more significant emission of the sample. It is not enough. We have done also 3 different test experiments. It is a PLE on a standard flake of MOSE2 on silicon oxide, so completely isolated with no contribution whatsoever from any quantum well because it's deposited on SiO2. We have also deposited a flake of MOSE2 on top of the bottom DVR to see any isolated contribution of the quantum well without the top mirror. And then also the standard PLE of the microcavity sample that you saw in the previous slide. So what you see here, this panel is this one. And what is interesting to see when we are looking, for example, when we are looking at the microcavity sample, always marking here the emission of the gallium arsenide quantum well, we can see that both the emission energy, the line width, and the PL seems to be insensitive to the presence of the quantum well. We are seeing, for example, similar phenomenology when we are studying the PLE on the flake deposited on top of the quantum well. There is no particular enhancement of the emission when we are hitting the resonance of the quantum well, only when we are exciting the tryon. And sorry, only when we are exciting the exciton and we see an enhancement of the emission of the tryon. And for the flake on SiO2, we observe the same thing. Only the exciton becomes much more stronger in emission when we are passing the laser resonantly on top of the exciton. So with this, I don't know if I have convinced you, but these are all the experiments that we have tried to do to see which is the role of this gallium arsenide quantum well on the whole picture of condensation with TMDCs. The input-output curve is done exciting with our laser resonant to the upper polariton branch. So what you can see here are the different dispersion relations for increasing pump powers, renormalized with respect to the threshold, which happens at around 15 milliwatts of pulsed laser measured in continuous wave. And in this panel that you see here on the upper part, what we are looking at is at this center of the spectrum at kx equals 0. And then what we are doing is to study the different properties of the emission in terms of intensity, line width, and energy position. So for the intensity, you can see a strong increase suddenly happening at the threshold. This is actually associated to a hysteresis that we have not fully characterized yet. But if you then increase up to, say, 10 times the threshold, and then you come back, there is a little bit of a hysteresis that is yet to study properly here. For the energy, it is a little bit surprising that in the threshold we are observing a sudden decrease of the energy position of the lower polariton branch, which we are explaining as an efficient trapping of polaritons in some trap of the monolayer, which is rather reasonable given the small size of the monolayer. And for the line width, we are observing also a sudden decrease from 16 MeV to around about 12, which we associate as well to the creation of a macroscopic coherent state. It's also interesting to see how does it look like the emission in real space. So what we have done here is to move around the sample, keeping the spot size on the cross. And you can see that, of course, you only get strong emission when we are pumping the monolayer. So this corresponds to the case of being above threshold and getting prominent emission from these TMDC polaritons. And when you move to other parts of the cavity, you basically get nothing or very, very small emission. If you want to observe simultaneously the real space position and the momentum space distribution of polaritons, it's also very interesting to see that when you're moving away from the monolayer, what you start to see is basically the naked cavity, which is slightly at a higher energy. More experiments on the gallium arsenide quantum well. One of the referees was insisting that probably what we were observing was pure phenomenology from the gallium arsenide quantum well, and what we did was to get far away from the flake and then do an input-output curve recording the different dispersion relations, and we see that when we are really strongly pumping the gallium arsenide quantum well via the cavity. So here we are pumping with 200 milliwatts, and I want to recall again that in this image, the threshold corresponds to 15 milliwatts. We are not observing any macroscopic occupation of anything at lower energy from the quantum well. So this has been all the different parallel experiments that we have done in order to understand whether the quantum well is having any role in this condensation or not. The last benchmark is to understand the coherent properties of the emission. So in order to do that, we have done a very simple Michelson interferometer, where one of the arms is retroreflected so that we can have horizontal and vertical inversion of the images that we are interfering in our detector. And the first thing to check is that only above threshold you are getting extended interference, which is the case that you can see here for a pumping condition of 9 times the threshold. And here below threshold, you are getting something that is simply having a very, very weak interference and concentrated around the bump spot. And the next point is to delay temporarily one of the arms by displacing physically one of the mirrors, as you can see here. And in this case, what you're able to assess is the temporal properties of your coherence versus delay. So you have here these 3 arrows that corresponds to these 3 panels, C, D, and E. C corresponding for no delay, 0 delay between the arms. And basically, we can see here that the temporal full width Hall maximum of the G1 corresponds pretty much to the lifetime of our polaritons. Okay. This is also kind of normal because we are pumping with a laser whose lifetime is much longer than the polariton lifetime itself. Another interesting thing to do is to assess that your polariton emission has an exciton component. If that is the case, you should be able to observe a Zeeman splitting when inserting your sample, when submitting your sample to a strong magnetic field. So these experiments at that time were performed still in Würzburg, where we were having access to this Atodry 2100, and you can apply a vertical magnetic field between ±9 Tesla. And then we have analyzed the circular polarization component of the emission in order to assess the sigma plus and minus polarization of light and see if there is any Zeeman splitting. So what you see here is the dispersion relation above threshold for 3 different magnetic fields, -9, 0, and 9 Tesla. And when you are computing the visibility of the circularly polarized light, as said, you can see that there is an overall change of color of the dispersion relation, which is associated to this Zeeman splitting. There are 2 things that I would like to say. The first one is that we are observing a decrease of the photoluminescence when we are moving far away from the 0 magnetic field, and this is something that we do not understand very well. If you have any comment or any idea, I would listen to you. But we basically observed that the threshold over the photoluminescence decreased quadratically as a function of the increased magnetic field, and it's not a very evident explanation, I find. The other difficult thing here is to associate an accurate Zeeman splitting, provided the line width of the polariton emission, which is really broad. As you can see here, this is 10 emitting, and the Zeeman splitting is going to be much smaller. So we have been obliged to do a very careful assessment of this Zeeman splitting. First, analyzing the spectrum at kx equals 0 for the 2 detection polarizations, sigma minus and sigma plus. From here, we have computed directly SZ, the visibility of the circular polarization. And overall, you see that the spectrum at kx equals 0 is going between, say, plus 0.4 to minus 0.4 as a function of the magnetic field. And what I'm showing here is this average value of SZ that we are averaging for all these energies when we are pumping above threshold and below threshold. It's relevant to see that below threshold, there is no a significant change of the average value of SZ, as you can see here in gray points. Then, from these two images, we should be able to see the Zeeman splitting, okay? It's not so easy, and in order to try to extract it, what we have done is, for every magnetic field, we have normalized Ks equals 0, the two spectra, and we have noticed that roundabout at the half height of each spectrum, it was noticeable, this small splitting in energy. And this is the criterion that we have used to put a number into the Zeeman splitting that we are observing in our polaritons, which, as you can see, it's around about 0.004 MeV per Tesla, really small. Okay, so with this, I finish the discussion of experiments at cryo temperatures, and if I have still time, maybe in 10 minutes, I can finish the experiments for room temperature.
Please go ahead.
Okay. For the room temperature experiments, we have been using a different sample. This does not have any hybrid microcavity, it's fully dielectric, so we are starting from a dielectric photon mirror composed again by titanium oxide and silicon oxide. Then we are depositing a different type of semiconductor material. This time is a monolayer of WSE2, in which you can observe an exciton at room temperature. The fact that it survives at room temperature is, and is not so visible at lower temperatures, is because a change between dark and bright states along as a function of the temperature. But this was our material of choice for these experiments. Then again, the sample is encapsulated with HBM, and then we deposit some PMMA. And this time, the mirror has not been deposited following the technique that I was showing before on scratching a mirror and then depositing it on top with dry etching. This has been in collaboration with the University of Viña, with the group of Falk, where they have evaporated the silicon oxide, titanium oxide mirrors on top, which is very practical, because this gives you a full top mirror on top of the whole cavity, and you don't get lateral emission that sometimes can contaminate your PL. Again, we are having a monolayer size that is rather small. This is around about 10 times 7 microns. So we can expect, again, polaritons to get trapped. And the Q factor of the cavities is much higher than before. It's almost 1 order of magnitude bigger, 4,300 or so. The first thing that we do, again, is to characterize the dispersion relation so that we can get a number for the Rabi splitting. What we can observe from this dispersion relation, which is obtained under non-resonant pumping with a green laser, is that we get some discretized polariton emission, which is explained very well with the theory done by Evgeny Zedon and Alexei Kavokin, mimicking the size of the monolayer piece, and considering a Rabi gap of 30 MeV and a trap depth of 15 millielectron volts. So we have had some difficulties to see the photoluminescence of the upper polariton branch, which is not present in this fitting at all, but this depends very much on the composition of your cavity. This is something that you will see if you design your cavity, so that when you are performing these experiments at very low excitation powers, only in that case, if your cavity is ad hoc for that, you can see the upper polariton branch. Otherwise, it might be difficult, as it is in our case. In any case, for those of you that might wonder whether this emission is only cavity or is only exciton, we have performed simultaneously both coherence experiments with interferometry to assess the photonic component, and also magnetic field experiments in order to assess the exciton component. So you cannot have only photons, you cannot have only excitons, it must be a hybrid particle between the two. Good. So Once we have measured the dispersion relation and we understand which are our upper and lower polariton modes, what we do is to insert again our sample in the Dry 2100, this time in a very extreme conditions. So you can see here what is the screen telling us. This is 8.1 Tesla at 993 Kelvin, thanks to the technology of AutoCube that we can get such extreme conditions for doing experiments. And what we do is to study the spectrum at kx equals 0 and analyze the two polarization components of the emission. And here you can see a much clearer splitting between the two PL branches, thanks to the fact that our polaritons are trapped, and you get much thinner line widths to analyze. We are associating a G factor for this polariton emission, which is basically the slope times the slope as a result of the product of the G factor, the magneton, the Bohr magneton, and the magnetic field, and this gives a value of 1.4. Okay, so we are sure now that our emission has an excitonic character, otherwise there will not be any Zeeman splitting. And then what we do is to benchmark the input-output properties, cranking up the power of our continuous wave green laser. This is the most problematic part of these experiments that we are doing, because you see that the input-output curve, when we are analyzing the intensity, it does not show a very evident or a very strong kink in the intensity that we get. It's a very soft S-curved shape, and we are associating a threshold power that is round about at 1 microwatt. You can see here the dispersion relation for these 3 different powers, and indeed you can see that the emission from this bottom part of the trap gets very, very intense, but it's not the same phenomenology as that we were reporting in this other graph here. It's a very big difference. Good. Next thing is to analyze the line width and the blue shift. The line width, same thing again. We are not observing a very strong reduction in line width when overcoming the threshold that we are naming at 1 microwatt. Here we should have a strong reduction of the line width, and it's not the case. And then for the blue shift, we are observing that there is a gradual increase of the energy position of the lower polariton branch, which increase much faster at higher energies. And this is not polariton interaction, this is charge accumulation, which has already reported in other papers from the group of Christian, and that we have also characterized by making this input-output curve up to here, waiting 30 minutes, coming back with the same power, and finding the lower polariton branch energy much lower, just because it takes some time in the order of hours to decrease these charges in the sample. Okay. We have also studied the polarization properties of this trapped state as a function of pump power, and when we are analyzing the linear degree of polarization, we see an overall increase as a function of the pump power, as you can see here, from 9 up to 17% for the 3 different pump powers that I was showing before. This is not so strange, because given the geometrical shape of the trap, it's natural to think that your polaritons will be oriented along the main axis of the trap. So we believe that what we were observing here was just the characterization of the geometrical properties of the trap, these H and V modes. Finally, in order to see that we are not having exclusively excitons, you have to demonstrate that you have an extended coherence of your emission, and this is where we did another Michelson experiment. You can see here, this time, energy versus real space of the delay arm and also of the reference arm. And here is the resulting interference between the two. You might wonder why we have implemented this experiment resolving our energies in the spectrometer and not sending our emission directly to a CCD, where we are not analyzing things versus energy. And the answer is because we are having all this upper emission, which is probably coming from weakly coupled excitons, or we don't know exactly what, but if we are integrating all these parts in energy and sending it to a CCD, then we are reducing enormously the available interference that we could detect in this bottom part of the emission. So this is why we are resolving energy. Again, what we are going to do in this interferometer is to understand the properties of the interference versus delay by computing the first order correlation function that we have extracted following a Fourier analysis that is very well described, if I remember well, in the thesis of Konstantinos Lagoudakis. Then what we have done is first to study the value of G1 in 2 different regions, which will be the bottom state here and all this other bigger area. And we can see overall, as a function of pump power, how this G1 increases. And also we have studied the coherence length of the emission that we are getting from these polaritons as a function of the pump power by fitting a function and associating a coherence length to this resulting Gaussian function that we are fitting spatially to these modes. And we can see, of course, that as a function of pump power, it's getting larger and larger. Finally, we are also studying the temporal properties of this G1 by varying the delay between the 2 arms. And this is what you can see here in this simulation. We are setting different delays. And you can see that only when we are very close to 0 delay, we are obtaining a visible interference between the 2 arms. This is 0, -1, 0 is the most visible one, and so on. Again, a study that has been done in these 2 different regions and where we can finally see what is the temporal coherence of this polariton emission. I would like to be very clear that for this second part of experiments, I'm not setting big words on condensation or lasing because the input-output curve is rather ridiculous, as we can see here. And there is not a narrowing of the line width, and the blue shift is not associated to polariton interaction. So we are being very careful in this work about which words we use regarding condensation or lasing, because there are some signatures of lasing, but it's not so clear. Okay. With this, this wraps up a little bit our results on bosonic condensation for cryogenic temperatures and for room temperatures, which are more or less there, but not so clear. And before finishing, I also would like to mention the results from Ki-Hua Kyung group, which this year they also reported room temperature condensation phenomena with WS2. You can check the paper and judge by yourself what you think about it. I will not do it. And with this, thank you very much for your attention. It was a pleasure, and I will take questions now.
Thank you very much, Carlos. Thank you. Very nice talk. A lot of results. So raise your hand if you have questions. I saw Helgi raising his hand first. So Helgi, who is calling in from Warsaw today, I guess.
Yeah, I'm still in Warsaw. Yeah. So thank you very much for the talk, Carlos. It's really interesting stuff. So
thank you.
Can we go to slide number 57?
57, here it is.
Yeah, it was about Zeeman splitting. Yeah.
Yep.
So, okay, so there's some G factor calculated, which is 1.4.
Yeah.
So I'm curious, what is the polarization of the excitation here?
It was linearly polarized. And
okay.
It's green laser, very far away.
Okay, so there is, all right, then it's there is no self-induced Zeeman splitting from the anisotropic interactions.
No. I recall that we were studying also these experiments, like trying to see if circular polarization sigma plus or sigma minus was inducing any detectable effect in this polariton emission. But to my memory, I think that these results were negative. We were not observing any particular phenomena, and we discarded it to show it in the paper because it was not very showing anything in particular.
Okay, thank you. I also have a question about slide 51.
51.
So I think if you had a question for us, so did I understand it correctly that your threshold was changing as a function of magnetic field?
Yes, quadratically. So basically it decreases. It increases. I need to put more power to reach threshold when my magnetic field increases. And also the photoluminescence, as you can see, it's much weaker. You are having here, I don't know, this is 1,200 counts, and this is reduced up to half the value. But I am not an expert on magnetic field magnetic phenomena, so we didn't delve too much into the results related to the magnetic field because there are many effects that come into play, and it's complicated. But the quadratic dependence on the threshold, this has been very clearly seen.
Okay. Maybe it could be explained if the scattering from the reservoir into the condensate is roughly spin isotropic. This is usually not the case, it's anisotropic. But if it were to become isotropic, then maybe it could explain the results, why the threshold increases with magnetic fields. But
yeah.
Okay. All right, and then I have
before we move on to your next question, Helgi, just on these results, since we discussed it, we published a paper, I think, together with Christian several years ago, Carlos, where practically that was in gallium arsenide structures, but in the presence of an external magnetic field, you have a tightening, if you like, a reduction of the Bohr radius. Yes, so you get the diamagnetic shift. And if you reduce your Bohr radius, as you were explaining in the beginning, you reduce the interaction between your excitons. So your thermalization processes, the scattering mechanism between polaritons is becoming less efficient, which means that you need to put more of them in order to reach threshold. And the diamagnetic shift has more or less, well, you need to check in your system if you would get this quadratic dependence that you observed. But you can go back, I think it is a scientific report of 2014 or something, blazing in Bose-Fermi gases, mixtures, paper together with Christian Schneider. Yeah. All right, Helgi, to your next.
Yes. So on slide 49, which was showing the coherence of the condensate. So the coherence, the autocorrelation point, it goes up to 0.2 coherence.
Yes.
Some people would argue it's not very coherent. So
no.
So I'm trying to get a sense of, is this still a good number, or is it what is the kind of standard for these systems to compare these results to?
So from the results of Quijua, if I show you here, I think that they were getting so actually, it's not in this graph, but I think the maximum that they were getting, it was like 0.6 or something like that.
Okay.
I have two things to comment. I think it's a great result, even if it's bad. It's only 0.2. We are used to see in gallium arsenide systems G1s of pretty much 1. But I guess that the number could be slightly higher if we had stabilized the interferometer, which was not stabilized. From there, you are still in a little bit of interference contrast, not much, but maybe 0.3. And the question about why is so low and not higher, and how can we improve it? I guess that the flake might be also better deposited, be larger, and then have the chance to study different regions. Because of course you can have regions where your exciton has properties which make the G1 be better. I don't know how to answer your question about whether it's a big or bad result, good or bad result. I think it's good. Whether it can be improved, definitely yes. And from Quijua, they have reported bigger values. I think it's 0.6. I can check the paper later, but.
Okay, it's totally fine. I mean, the data shows the contrast outside and within the pump spot, so it's clearly there's something coherent happening. And my last question is on slide 4.
Sorry, again, Helgi, before we move away, there is another start. There is a start point here. The fact that your coherence is shorter than your excitation pulse.
Yeah.
And you will remember the works in 3-5 polariton condensates, where the coherence exceeds practically the cavity lifetime. It is not limited by the cavity lifetime, it is limited by the interaction strength. So here you have reported an interaction strength, which is, I mean, if you were to be polariton interaction limited in your coherence, you would have a much longer coherence. Yes, you would be going to tens of picoseconds. Mm-hmm. Here you are reporting a coherence which is sub-picosecond. Mm-hmm. It is matching practically your Q factor. So it is not driven by polariton-polariton interactions. Clearly something else decoheres your system. And that is an indication of that someone could argue that this is an indication of weak coupling. Yes, you are now in the weak coupling regime,
which is perfect. Yeah, which is expected because the Q factor is.
Yes. So you are driven by the Q factor of your cavity. This is a laser in a cavity of a very weak Q factor practically, and then and that's the direction. One would need to argue why this is not weak coupling lazy now. And it is still strong coupling, but not limited by the interaction between the polaritons that would give you a much longer coherence time.
Yeah.
What are your views on this?
I think that I agree on what you are saying. If we mention here, if we reported in this case that the temporal line width of the G1 is around about 0.4 picoseconds, the full Wilhelm maximum. This is slightly longer than the polariton, than the exciton lifetime. The cavity lifetime, I don't remember anymore. What is the value? Let me see if I have it. Not sure how to answer your question, Pablos.
We can discuss it. We can discuss it later. Helgi had one more question before we move on. I can see that there are many more questions coming up. So Helgi, please.
Yeah, last question. So it's on slide 45. Mm-hmm. So this really. So what was again the Q factor of this cavity? Was it 500?
Yes.
Okay. Isn't it a bit strange to see such a really abrupt jump in a relatively low Q factor cavity? Because if I remember correctly, when the lower the Q factor, the smoother the transition, you go from non-lacing to a lacing state. But here you have a very sharp jump, which is kind of reminiscent of high quality cavities. Mm-hmm. So I'm wondering, is there something inherent to the TMDs that's causing this kind of a sharp jump in the PL?
I don't think so. I think this is the fact that you have a very sharp jump is something that we have attributed to a hysteresis. And maybe Pablos can complete here my answer, but I don't know if hysteresis is exclusively something linked to high quality cavities. Now I cannot recall. I do not remember, but this strong jump is just reporting only one branch of the hysteresis curve. If I was going down now in power, you would see the other branch happening at a lower pump power. Mm-hmm.
Okay. Okay, thanks. Well, maybe that because you say hysteresis, have hysteresis normally been observed in the integrated PL of these polariton systems? Because I'm familiar with optical bistability under resonant excitation, but is this related to that? Is this optical bistability that we are observing?
Yeah.
Okay.
Okay, thank you, Helgi. So let's move to Tamsin, who raised her hand second in the row. So Tamsin, please go ahead.
Hello, thank you for the nice talk. Could I ask a question, first question about slide 58?
58.
I think it was.
Here it is.
Yeah, so these higher modes that are at 1.64 and 1.66, yes. Do they increase linearly? Because we've only seen the intensity curve for this lowest mode.
I don't know if we had the analysis of the intensity increase for these modes, but I think that we explained the origin of these modes as cavity modes that are not coupled at all to the monolayer. And
they would increase therefore linearly with pump power.
I guess so. Let me see one thing, because I remember to have when we are reporting. I don't have here the slide, but what we have done in the paper, this is something that if you wanted, you could check as well, is to see whether the emission that is arising from this point and shows any change of color when we are computing a set. So you could see whether it's fully photonic or it has any excitonic component. If I recall well, the change of color on the visibility of the circular polarization only happens for this part. So this is what we are talking about here. It's just cavity modes that are not coupled to the monolayer.
Okay, I will check as well and have a look. But the other question I had was on, I think, slide 60.
Yeah.
So if I understand correctly, you excite with linear polarization, and then you have a very clear degree of linear polarization in your emission that's half vertical, half. So when you then on the next slide compute or measure the G1, is this polarization resolved? Or are you interfering both the vertical and the horizontal polarization with each other?
Yes, we are.
This could reduce your G1 quite. If you have this fine mode splitting, these modes would compete in the G1 and cause a reduction, surely, of your G1 factor in the, I think it's the next slide, shows the G1 that you measured.
Yes, you are right. In this case, we are analyzing the linear degree of polarization, simply turning a half-wave plate and a linear polarization in front of the spectrometer. But when we are performing G1 experiments, we are not post-selecting any polarization at all. This the emission as it goes directly into the interferometer. Post-selecting in polarization, I guess that of course it would increase the observed G1, but I guess that it's more reasonable to send everything into the interferometer and see what it comes from it. No, I mean, post-selecting in polarization, I think would be a way of artificially increasing the G1, right?
Oh, possibly, but it's also possible, since this is fine mode structure splitting, that they're slightly out of phase. And if you measure both, that you have a higher G1, that they're slightly out of phase, causing, when you measure all of it together, an overall reduction of your G1.
That is right. But in a way, because we also observe that these two linearly polarized modes have slightly different energy, as you can see here.
Yeah.
We are actually, in a way, post-selecting in polarization with the spectrometer, because we are separating all the components into energy, which is mapping into polarization in a way, because these modes have different energy. So in a sense, we have been doing what you are suggesting, like resolving different polarizations, but in energy.
I see. And my final question was, when you then put this system into the magnetic field and have the Zeeman splitting, I cannot remember what slide that was on. I'm very sorry.
Is this one, this sample, or?
Yes. Did you measure the G1 as a function of the Zeeman splitting and how it changes under this situation?
Sorry, I think I gave a very, very poor explanation when I was going through this slide. So G1 is basically times the Bohr magneton is the slope of the dependence that we are measuring here. So we have two spectra that we are recording as sigma plus and sigma minus. We detect the splitting of energy that we are plotting here, and then the slope that we are retrieving here is directly this product.
Yeah, no, I didn't think the G-polariton was the G1. I was asking if you measured the G1 as a function of.
As a function of the magnetic field? No.
Yeah.
Too much work.
Okay. I always just be interested to see how the G1 changes when you have this increase in Zeeman splitting.
Super interesting. I think it's super interesting experiment. But when we did these experiments, we had to make a trip to Würzburg in order to implement these measures, because we are not having yet this cryo system. And it was 1 week of measurements. And as you can imagine, it's a single shot rushing to do the experiment that you need. So indeed, it would be super interesting to mix magnetic field and G1, but it was out of the time that we were given to do this experiment, unfortunately.
Yeah, I understand that would be quite a lot in just a week. Thank you very much, and thank you for the nice talk.
Thanks to you.
Thank you, Tamsin. So Dmitry Dovchenko from Southampton.
Thank you very much for an interesting talk, Carlos.
Thank you.
I have a rather technical question about relative both experiments, both samples. Have you engineered the sample the way that monolayer would be in a specific place relative to the field distribution inside the cavity, or is it just on the surface? Because the PMMA deposition, like step by step, will allow to place it basically anywhere in the. So
we are also using the cavity configuration, which is allowing us to deposit the monolayer directly attached to the bottom mirror. So you have to choose the upper pair of your Bragg mirror, so that the optical mode is going to be attached to the two sides of the cavity. Then you can get a perfect overlap with the two. We have seen that this technique that we have here is in general working well, so that when you are splitting the mirror and then you flip it back to form the cavity, you're gonna have the good size or the good element in the inner part of your cavity, so it's gonna be symmetrical and you're gonna get the mode as it should be. But yeah, all our cavity configurations are such that the optical mode has a maximum in the interface when the DVR starts, so that the monolayer is overlapping.
Yeah, thank you. And also rather technical, maybe I missed, what was the thickness of the PMMA layer between the...
Yeah, we have done several calibrations as a function of the concentration, and in general, the target thickness that we are having now with the current samples that we are generating is around 100 nanometers.
Yeah, okay, thank you.
Welcome.
So we also have a question which I'm going to read. It comes from Sihem Jaziri, and the question is that in the case of tungsten disulfide, diselenite, what is the effect of the dark exciton?
Oh, wow.
Have you seen any the role of the dark exciton in the measurements you did?
Yes, we've got a very similar question from the referee actually. We have been studying very, very carefully what is the presence, whether there is any presence or no. This question is about the dark exciton, right? No, the question that we got, it was about the presence of the bright of the tryon, and the tryon plays no role. About the dark exciton, we have just submitted a paper in which we are observing brightening of the emission of these polaritons when we decrease the temperature, which comes from an interplay between the relative position between the bright exciton and the dark exciton. So as you decrease the temperature, because of the modification of the position of the lower polariton mode with respect to the dark exciton, there is a change on modes that are available. And yeah, there is a paper that we just submitted very recently. Unfortunately, it's not in archive, but there is a study that is going to come up, which is based on this sample. So yeah, it's very interesting to study the interplay between the bright and dark excitons in this sample as a function of the temperature.
Thank you. We have one more question from Anton-Solanas from Vienna.
Yeah, thank you very much, Carlos, for a nice talk. I have a question. If you go on the slide number 43. I have 43. Yeah, I noticed you have a little bit of asymmetry in the population of the low polariton branch. Why is that so?
Yeah. I don't know where is the symmetry coming from. I have wondered myself the same question. I will be a little bit. So the asymmetry you're referring to the lower polariton branch or the gallium arsenide quantum well?
Lower one, yeah.
Yeah, I mean, this fitting is a little bit MacGyver. You know, I've been used to work with gallium arsenide semiconductor samples, and it's a totally different story. When you're working with TMDCs, you have to open your mind a little bit because the languages are much broader, and the fittings that you do are a little bit different. So if you're asking me now about the asymmetry of the lower polariton branch, yes, indeed, it is different, but this is the material that we are using, and this is the best we can do in order to fit the modes. Yeah, I mean, it's funny that you're asking me about this dispersion relation and you're not asking me about the fitting of this one.
Yeah, but, I mean, this was my next one, but okay.
Yeah, this is the same. I mean,
I see. And there is a kind of signature of the bottleneck effect. Is it correct? My understanding there in the previous slide.
You are talking about
the accumulation at the high K, the population. There. If you go, is it the bottleneck?
I'm not sure. I don't know if it's the bottleneck or it might be that the excitation, which is coming relatively close in energy here, maybe the pump is coming with a slight angle, and that is motivating a bit more of photoluminescence in one side of the lower polariton branch than the other. I don't know if it's a bottleneck. It would be too beautiful to be true. I think that what you see here is the spectral filter starting to kick in, and this is why you see a decrease of the PL here. That of course we have to use to remove the laser.
And you also mentioned a little bit that in principle to claim the BEC or so, you need to show thermalization behavior. I was wondering what actually that prevents you to study thermalization as well.
Yes. In this sample, the one at cold temperatures is the shape of the emission that you can see here. It's pretty difficult with this broad emission of the lower polariton branch to give a clean analysis on the Bose distribution at high pump hours. It will be also even more difficult from the fact that we are setting a spectral filter here because we are pumping the upper polariton branch. So it will be a figure that is not nice as compared to the one of the paper of Kasperczak, where he can see all the energies because he's really pumping non-resonantly. And in the case of the sample at room temperature.
No, okay, here I see it's at the trap you can't really understand.
Here, there is no really change of the language, so this is why in the paper we are not even using the word of condensation.
And since we're here, can I also ask what's the threshold in terms of absorbed pump power, absorbed fluence?
The threshold in terms
of absorbed fluence, the fluence in the system that you put in the system. That energy per micrometer. So
the density of power that we are using. I don't have the number in mind, but at threshold we are associating it. We're associating the threshold at 1 microwatt, and the pump spot has 3 micron or so size. So from there, I have not done the conversion to see what is the number of polaritons associated to that. This counts. This different derivation of how many polaritons we have at threshold is something that we have to do carefully for the system at cold temperatures. But at room temperature, we didn't even try because there are other more strong features like absence of line width narrowing, which do not allow us to talk about the threshold, basically.
I was also wondering what's the exciton fraction of this in this case, room temperature system. Because it seems like really very much
photonic. Yeah, it's very photonic. I want to believe that this number is indicated in the paper, but I don't have it in mind at the moment. But it's going to be pretty photonic.
And do we have any issues with photostability here?
Photostability?
Yeah. Does it degrade the sample?
We have observed indeed. So this sample is something that is a sample that is turning around since a couple of years now, and we are still using it. We see that it becomes dimmer as a function of this effect of charge accumulation. But every time that we come back to it, I would dare to say that it's not suffering from phototoxicity. And the mirror deposited on top, the evaporation is also pretty stable. So we have not observed any degradation of the sample in none of the two, actually, because from the moment you're encapsulating them with HPN or even depositing a mirror on top, this is pretty well protected for the rest of the time.
Okay, I see.
Is it something that you would? Is it something that you would expect? This degradation?
No, I'm just wondering because my expertise, for instance, lies in organic systems, and I try to see advantages and disadvantages of different systems.
Right. So yeah, definitely we are also working with mCherry, and there we know that once you make your sample, you have it for a month, and then it's gone. Yeah. And if you do an input-output curve, you can expect that after you are finalizing the final pump power, it's going to be gone, your sample at the highest pump power. In this case, in TMDCs, I don't think so.
Okay, it's very stable in that sense. All right. And just the very last question, more like conceptual. What do you think is the blue sky of all this research? What are the next steps, and where does it go with room temperature TMDCs and stuff?
Yeah, so in the immediate experiments that are coming, and that we are planning to do very, very soon regarding the first sample, this one, this is going to be observing the G2 of the emission. We are trying to see how thermal or coherent the emission is. And we want to measure as well very carefully this stability that we were observing in the input-output curve, what I was talking here before to your colleague. For the other one at room temperature, where is it going? Well, I think that the very first step is to make flakes which are bigger and that are spatially more homogeneous. And then from there, I guess that the next step will be to follow the direction on exploiting the nonlinearities that make a real difference with respect to the 3-5 semiconductor microcavities. I think that this is the place to go, to try to exploit the fact that GS is much, much bigger than standard semiconductors. And maybe there are some applications to think about how playing with the quenching of the Rabi splitting can give you more sensitivity to detect something at room temperature.
Mm-hmm. Sure. Thank you.
I don't know if it's going. Yeah, I don't know if it's going to be at the level of competing with the results of Pablo's, where he has observed this single photon level detection. Maybe it's going to be a different system or a different idea, but I think that controlling nonlinearities at room temperature is the way to go. And I think that TMDCs are promising for that purpose.
Thank you, Carlos. Back to the room temperature results, where you measured again with your Michelson the G1.
Yes.
So if you go to the time delay of the G1.
Yes.
So you had somewhere G1 as a function of power as well, if I remember well. Somewhere
here.
There you are. So at 1 microwatt, G1 is 0, but at 1 microwatt is where you decided to define threshold.
Yeah.
So what are the criteria that you use to define thresholds?
I think that a proper way to do that would have been to fit a line in this area and fit another line in this area, and then where they cross, that will have defined a proper better threshold. I think in this case, because we were observing such a faint S curve, the determination of the threshold was very much approximated, so to say. It's not. There was this mismatch, as you say, with respect to the experiments of the G1. So it is more or less the place where we saw this change on the curvature of the curve. But it could be 1, it could be 2, roundabout.
Okay, and also I had a question regarding this power dependence of G1, which so if you can, yes, on the slide where you have the power dependence of G1. Clearly, when you go to lower powers, your emission intensity from the sample is weaker. Were you increasing the integration time, or was G1 also dropping because of signal to noise in your spectra?
Yeah, we have to take a lot of care.
It's not changing. The line width is not changing. And practically, you expect that your G1 will be proportional to your line width. Yeah. So
Yeah.
I'm not. It is strange that you see an increase of G1 when the line width practically remains the same.
Yeah, it's a very good point. We have been verifying that all these error bars that we are including here are describing very well the signal to noise ratio. So in that sense, if we were having just an artifact on the decrease of the G1 just because we are increasing the noise level, then the error should be much bigger. And we have made a lot of attention to see that we are having a very distinguishable peak from the background, and that from there we can properly extract a number for the G1. At the same time, you are right. If the line width is pretty much the same, there is actually a slight increase, not really, but if there is any signature of condensation or lacing is really weak, and this is the problem that we have had with this paper, right? There is not there are signatures for lacing, but at the same time, when you are going into the region of low pump power excitation, G1 is low, the line width remains pretty much the same, but don't know what else to tell you, to be honest.
That's okay. Carlos, I'm afraid we are running out of time. This has been 1.5 hours, and we had 30 participants in this in your seminar from around the world. So I would like to thank you again very much for coming.
Thank you very much
today, and thanks to everyone who joined our seminar today. And we are looking forward to see you, and you, Carlos, if you can join us next week, where Thilo Stoerfeld from IBM will be giving a seminar on organics. Yeah.
With pleasure.
Okay.
Yeah, thank you very much.
Thank you very much, everyone. Have a very good day.